So are you speaking anything? Because I think your mic is off.
Video is off.
Uh,
Now am I audible?
yeah, you're audible now. We haven't been able to hear anything from the starting.
Okay. Sorry. I could not got that. So slides are moving. Okay.
Yeah, slides are moving, but the audio wasn't.
Okay. Now it's audible.
Yeah,
Okay.
it's audible now.
No problem. I'll just start from the beginning. So as I discussed that diffraction will the process by which a beam of light passing through a like small orifice in a the Young's double slit experiment. So when you have light passes through this orifice, you will able to see the constructive interference. Then only you will able to see a peak. That means that all are in a phase. You will able to see a constructive peak. If it is destructive interference, you will not able to see any peak. So this was the Young's double slit light experiment. So that was there. So similarly, if you see in a Wechsler diffraction, so the diffraction occurs in the similar fashion. So here, that as you know that scattering when radiation fall in a material, so that scattering can be possible in any directions. So there will randomly occur, but the diffraction is a subset of scattering. Wherever the Bragg's law satisfied, then that means when you have a light is falling on a crystal, there in lattice planes are here, the yellow lines, you can see. So they are going in a particular phase. If they are in phase, you will be able to see a diffraction. And this diffraction and interference, they are interrelated. If you see that when your phase difference is 0 degree, that means your red peak and this black peak, they are in a phase. That means you will be able to see a constructive interference. If they are in not in 180 degree phase difference, that means red and this blue one, they will cancel out each other. You will get a destructive interference. That means you will not able to see any diffraction at that position. So that means diffraction occurs when light is scattered by a periodic array with a long range periodicity. That means your light, or you can say X-ray, that passes through a long range, periodic array with a long range ordering. Then you will be able to see that interference. So if you see the background, that history of X-ray diffraction, in 1895, that X-ray was discovered by Rontgen. if you see, this is the image of Dr. Röntgen, and this is the schematic showing there is a ring on this, hand. So that was this is the hand of the Röntgen's wife, and she was wearing a ring. So you can able to see, identify that particular ring with by the X-ray diffraction pattern. So this is the first X-ray, photographic image that was obtained by Röntgen. Then you have Lau give the principle of diffraction pattern in 1944, and so in 1915 Bragg's theory come into picture. So that is the basics of X-ray diffraction. Then powder diffraction was developed in 1916, 1917, that in Germany and US. And first commercial diffractometer, so this Philips PW 1050, so that was discovered in 1947. And then by using this, this X-ray diffraction, so DNA structure solved by Watson and Crick in 1953, for which they got the Nobel Prize by using single crystal exciting. So X-ray diffraction has a similar principle to multiple slit experiment, like Young's multiple slit experiment. So it's similar principle, and constructive and destructive interference pattern depend on the lattice spacing and wavelength of radiation. So that we'll see the next slide. After a few slides. So this I have already discussed in last class that X-ray is produced by striking high energy electron beam on a metal surface. So this is the tungsten filament where because of high voltage harmonic emission of electron will occur. Then this electron will fall on the target filament, that is target copper anode, from where you are able to get the X-rays. And the whole thing is sealed in a vacuum. As you know, you will get two things from X-ray radiation. One is your continuum spectrum, that is Bremsstrahlung radiation or background radiation, and some characteristic peaks. Those characteristic peaks are either coming from either K cell to L to K transition K alpha, M to a K transition M, K beta, or K gamma from N to K cell, and so on. So you will get all these characteristic peaks. In these transitions are from one level to the other. So they define a particular characteristic of that element. So these are characteristic peaks respect to the element. Like copper has like K alpha is 1.54 angstrom. For molybdenum it's 0.07 angstrom. So for defined element that K alpha characteristics, that wavelength is different. And you know that when you go for an excited diffraction study, so first of all you remove the K beta by using filter. That Z-1 principle I discussed, that if your target is copper, then filter should be nickel. The atomic number should be Z-1, previous one you will use. And then K alpha, K beta will be there, it is quite overlapping each other. So in conventional XRD, you can't differentiate between these two, but by using high energy synchrotron source, you can able to eliminate K alpha 2. So this characteristic peak is mainly that is important for X-ray diffraction studies. As I told here, that filter you can see for molybdenum target, you have to take zirconia filter. For copper target, you have to take nickel filter, and so on. And for another thing, that some of this, the target material. So in presence of other, like for example, if you take a Fe3O4 or any iron-based material in copper target, sometimes copper with presence of iron is autofluorescence will come. Fluorescence will come from iron. So because of that, you get a lot of background. So accordingly, you have to choose your target element to find out your proper X-ray diffraction. You can see here by using a nickel filter, because the absorption maxima of nickel here it lies in the K beta region. Here is the cutoff. So you can easily remove this peak, and you can able to see only K alpha you can able to take. So coming into X-ray diffraction, so all these, that X-ray, the resource and all those things are main requirement that copper we take as a anodic material, and tungsten filament was there. And then if you come to atomic planes of crystal causes, if you have this is a substrate, and then in this substrate you have if you take this is a substrate, on this substrate there are lattice planes. Okay, so if you have lattice plane, they are periodic in order, and the atoms are periodically arranged on this each lattice plane. So atoms will be periodically arranged. So what happens when the atoms are critical. Then your X-ray is falling here. For example, X-ray is coming, then it will diffracted into the other direction. You will see. So incident beam, it is incident beam, and your diffracted beam making an angle 2 theta with the transmitted beam. So this is the angle of diffraction that 2 theta will take. So mostly atomic plane of crystal causes incident beam X-ray to interfere with one another to leave. Then they leave from the crystal. They will interfere with these atoms and they will come out. So based on the whether it is a constructive interference or destructive interference, you will get the diffraction peak. So it is a non-destructive technique, but in XRD you can recover your material. So this is a non-destructive technique. Mainly you identify the crystal phase and its orientation. So it measures the D spacing. You can get D spacing, lattice parameter, crystallite size, phase composition, atomic arrangement, stress, etc. That means if you have prepared an unknown material, you can identify that material by using X-ray diffraction techniques, and it will mainly give D spacing. From D spacing, and that you will get this type of spectra. From there, you have a peak intensity and peak position. From there, you can identify the different like parameter even by using the analysis. We will discuss later. So you can find out lattice parameter, then crystal structure using Device-Error formula, and atomic arrangement. All this you can find out. So mainly it gives crystal structure of an unknown materials. And a detection limit up to 2 to 3%. If there is a two-phase mixture, for example, if I take a silica in quartz and as well as its amorphous phase, that you can identify that within a detection limit of 2 to 3%. Like copper oxide, if you doped with zinc metal, whether the zinc composition is within 2 to 3%, that can be detected by this conventional XRD. But if you go for a synchrotron high radiation, even at very low concentration, 0.1%, you will able to see the crystal structures. Mainly, you need a coherent, monochromatic, and parallel waves for the construction of a constructive diffraction pattern. So you can able to identify the particular crystal structure. So for XRD, the Bragg's law is the basics of the X-ray diffraction principle. So whenever the Bragg's law is satisfied, that means n lambda equal to 2d sine theta, then you will able to see a particular peak. So if you see here, this is the red line is the crystal plane on which the two X-ray 1 and X-ray 2 are falling. You can see that after falling here, you can see this is the angle theta, it's moving out. And the second one is coming here, and if you draw a perpendicular from here to first plane to the second, that this. So this is the phase. If you see here, here to here, here to here, and here to here, distance is same. The distance traveled by the light is same up to here. Again from here to here is same. The only difference is this much in this side and this much in opposite side, this side. So that is nothing but if this is your theta angle, then you can apply that equation. You can get d sine theta is this distance. So here is d sine theta is d sine theta. So 2d sine theta is the phase difference. The 2d sine theta that should be equivalent to integral multiple of your wavelength. N lambda equal to 2d sine theta. N can be order of reflection, the first order n equal to 1, second order n equal to 2, and so on. So whenever this law, Bragg's law satisfies, then you will able to see a diffraction peak. So since sine theta can't be more than unity, so n lambda will be always less than 2d. So lambda should be always, you have to take wavelength is always less than that of 2d. As you know that most of the d spacing when you go for inorganic system, so that lies in the the angstrom level, and the copper K alpha target we are using for commonly using for X-ray, that is about 1.5405 angstrom. So if this wavelength, if you see 1.5405 angstrom, and that wavelength, the lambda, that copper K alpha lambda, you are taking this, and this is within the 2D, that 2D limit of the lattice spacing between two planes, so you'll able to see these things. So path difference must have integral multiple of lambda wavelength. So this is the equation n lambda equal to 2d sine theta. So you can rewrite the same equation like sine theta. If you take 2 in opposite sides, lambda by 2 by d HKL. Okay, so you can divide here d. If I have taken n equal to 1 in this case, so sine theta, lambda equal to 2d sine theta, then sine theta equal to lambda by 2 d HKL. So d HKL, I can write 1 by d HKL the lower side. So you take it off, so you will get equation sine theta equal to 1 by d HKL by 2 lambda, which is modified Bragg's law. So sine theta equal to 1 by d HKL into 2 by lambda. So because when you go for a extra diffraction analysis, what you get, you are getting a diffraction pattern, but that diffraction pattern is generated from the diffraction spot that obtained in a reciprocal lattice. Okay, so from the reciprocal lattice, you are converting it to real lattice, and then you are getting that. This all those things are now taken care by the software, and you get a diffraction peak you are getting. So if you want to see how it happens, first you draw a circle of this is 2 by lambda is d, that here, so you circle with the diameter 2 by lambda. So this is my circle, this is my circle, which 1 by lambda is my radius. Then I will get a circle I will get, and then I will put I'll draw a triangle P, a point on the circle. It's like a P, a point on the circle, and then A to P I will join with O. I will get a triangle, construct a triangle with diameter as a hypotenuse, and 1 by d HKL. This 1 by d, that this is as your one of the side. This is your side, and this is 1 by lambda. So total will be 2 by lambda is diameter, and this is your AP, that hypotenuse, and this is your 1 by d. So the angle opposite 1 by d side is theta HKL. This is your theta HKL. Now you put a crystal plane here. This is your sample here. You incident beam is falling on this direction on the same circle you see, and is diffracting in this angle theta. So here the P is the point that lies on this whole sphere. This sphere is a reciprocal lattice that will call it a Ewald sphere. And this Ewald sphere, the point which lies, that is P point, that lies on the Ewald sphere, then only you will get that particular plane. If the another plane is lying here, this plane, so then you will get that particular plane. So wherever a plane falls on this Ewald sphere, you will able to get a diffraction spot. So that modified DHKL, you can write this way. So if you see here that Ewald sphere, so you can see, as I told, that the S0 is coming the incident ray, and this is your the diffracted S1, that's 1 by D this. Then you can see this is the Ewald sphere circle, and this is the point 101 lattice, and that falls on this particular ring. Then you'll be able to see that particular 101 peak in the diffraction pattern. Since 201, 01, 001, they are not falling on this ring, you will not able to see that diffraction plane. So then you have to orient your the circle that such a way that maximum number of plane falls on this, you will be able to see that diffraction pattern. So as I discussed that whenever your particular plane falls on the Ewald sphere ring, on the surface, the surface of that ring, you will be able to see a diffraction peak. And if you take the order of reflection that I told n, that n lambda equal to 2d sine theta, if you take here n equal to 1 for sine theta, but if sine theta is 0.2 example I have given, the first order reflection plane of 110, you will get 20.7 degree. And the same second order reflection plane of 100, you will get 43.92. That will be the first order plane for 220. Since second order plane of 110 is equal to the first order plane of 220. So if you see the D spacing, T110 A by lambda by 2 and 220 equal to A by lambda by 8. That means if you divide this 220 by 110, you will get a 1 by 2 ratio. That means if nth orbital, nth order it will take DHKL and DNH, NK, NL, that will be DHKL divided by N. So N is your order of plane, like you take fifth order plane. So fifth order plane HKL value, the DHKL value will be D, whatever the DHKL of the first order plane divided by 5. That means nth order reflection from HKL plane of spacing d may be treated as a first order plane for nh, nk, nl with d spacing d dash equal to d by n. That means the first order plane of a particular plane can be equivalent to that is lower order plane. That means you see the second order plane of 110 will be the first order plane of 220. Similarly, if you go to third order, fourth order, they will accordingly change. So you will get a relation d nh nk nl equal to d hkl divided by n. So if you see, but when you go for an X-ray diffraction pattern, sometimes you see there are missing plane. You are not getting all X-ray patterns. Like, as you know, the Bragg's equation is a negative statement. That means if Bragg's equation is satisfied, you may get reflection. But if Bragg's equation is not satisfied, there is no reflection. If not satisfied, then it's no is coming, no reflection. Okay, so if it's satisfied, you may. That doesn't mean if Bragg's law is satisfied, you'll always get a reflection, always get a diffraction pattern. That is not the correct statement. So therefore, the Bragg's equation satisfied. Thus, even though Bragg's equation satisfied, reflection may not observe. For example, you will see here, this is a molybdenum VCC structure. You can see that green wave, this plane is coming here, diffraction. This is it, and center there is a red plane. So what's happened? But if you see that the wave started from the middle plane, if you see this is the first top plane, you can this, and this is the bottom plane, that green one. So they are in a phase. If this and these are phase, you will able to see a constructive interference, and you will able to see a perfect peak. But in the middle plane, if you see here, that is in the opposite phase. That is phase is not a lambda. This phase difference is lambda by 2 here. Since it doesn't satisfy that phase relation, this is this peak, you will not, that is this from the center plane, you will not able to see that particular reflection. That means 100 plane in reflection of BCC molybdenum structure. This is a BCC crystal at the center atom here, all corner atom are there, and this is BCC. So 100, that is missing. So but this is similarly, if you see NaCl and KCl, which one will give more number of reflection? Can anyone tell? So if you take NaCl and KCl, okay. So if you see the structure, this is the NaCl structure, okay, and you can see here, and this is the KCl structure, okay. So the difference you see, NaCl, this is your sodium atom, and this is your chlorine atom. So you can see here that the structure may be thought to be two interlocking Na plus and Cl minus. It's a closed packed structure, FCC structure, NaCl. So if you see the particular, this atom, they are in different in size. But if you see this K and chlorine, these two red and green, so they are almost equal in size. So that means that Z value, that they are isoelectronic. So if you see, since the chlorine has 18 electrons, it scattered X-ray more than sodium. Sodium has 10 electrons. Okay, if you take NaCl and you draw that Na plus Cl minus, and you will see here that to the octet satisfaction, it is that 10 electron, here it will be 18 electron. So being 18 electron, that reflection will be much higher in case of Cl minus. So because of that, so there will be a difference Na plus and Cl, since though they are parallel interlocking to each other, so you will get a net result. So you'll be able to see that 111 peak. But in case of KCl, you can see in NaCl, this 111 peak you are able to see. But in KCl, they are isoelectronic. Both are isoelectronic. We will discuss later the structure factor. That means how much that the X-ray will be scattered from that Na on Cl or K and Cl. So if in K and Cl, that that structure factor, that scattering will be same. So because of that, they will cancel each other. That 111 peak you will not able to see in case of KCl, which you observed in case of NaCl. But the same thing will be different if you take a neutron diffraction pattern. But in neutron diffraction pattern, you will able to see this KCl, that 111 plane, that we will discuss when we go for a neutron diffraction study. So if you see the selection rule that in general that common selection rule that how if the Bragg's equation is satisfied, reflection may go missing. So this is due to the presence of additional atom that you see in the BCC structure molybdenum, that center atom. So if a simple cubic, the reflection is possible. All HKL value is possible. Oh, reflection necessarily absent? No. But in the body center cube, is BCC structure, H plus K plus L has to be even. In case of phase center, H, K, L unmixed or all even, then only you will be able to see a diffraction fix. That means if you derive the ratio of H square plus K square plus L square based on the extinct rule used in the determination of what is the FCC structure, BCC structure, simple cubic structure, or hexagonal cubic structure, diamond structure, all these structure can be identified based on the H square plus K square plus L square value. In case of a simple cubic, that all HKL will 1, 2, H square, that like H square plus K square plus L square, 1 can be possible, 2 can be possible, 3 can be possible. But in BCC, you can see that is like 4, 5, 6, 8. Here it is different. Here it is, this place is 7. Similarly, FCC 3, 8. So all these extinct rule is allowed. If you see here, the S square plus L square, that plus K square plus L square, if you see that 7 and 15, these are the two S square plus K square plus L square is not possible. You can't get any plane. Like for example, if you take 1, so that may be plane maybe 1, 0, 0. You can get 1, 0, 0 plane or 0, 0, 1 or 0, 1, 0 plane is possible in simple cubic. In 2, 1, 1, 0. In 3, 1, 1, 1. 4, so 1 square plus 1 square plus 1 square will get 3. So here 2 square equal to 4. So 2 square plus 1, 5. But in 7, you can't commute it into this H square, L square plus K square plus. Here 15 is not possible. That's why all this you can't express this. Therefore, no plane is possible in this case. Okay. So if you coming into diffraction method, so far I have discussed the basics of X-ray diffraction. And if you come to the diffraction methods, like there are 3 more commonly used methods. The first one developed as Lauk method, then it's a rotating crystal and powder diffraction. So the rotating crystal is nothing but this basic principle of single crystal XRD, then you have powder XRD. So in case of Lauk method, the wavelength is variable. Here wavelength is variable, but angle is fixed. So you can use a single crystal analysis by using a different wavelength. A rotating crystal, you have a variable, you have a fixed wavelength and a variable angle. So you can, your crystal will be, your wavelength will be fixed wavelength, and you can vary the angle, you can vary. Similarly, in powder diffraction, you have a fixed and wavelength and vary. Like in case of copper, you have 1 point with copper K alpha you take, and angle is variable, and you will get in a powder in case of powder diffraction method. So Lauk method mainly used in single crystals to determine the crystal orientation and quality of the structure. So the rotating crystal method again used for the unknown crystal identification. Like if an unknown crystal, you have to go for single crystal XRD to identify that structure. And then if a powder diffraction, there is a many orientation is there. The sample is composed of a polycrystalline material. It's not a single crystal. You have many crystals are there, and then these crystals you will see that identification of identical lattice parameter with high precision. You can use a powder diffraction method. So if you see the X-ray diffraction, this is the old age we use this this powder X-ray diffraction method using Debye cone. That there is a Debye, there's a strip. On the strip you will get, if you see, this is your sample here, and this is a thin film that is surrounding that sample. You can see that this is a very thin film, and there is a hole here. There is a hole in this side. Your X-ray is coming on this, falling on the sample, then it's scattered, then it diffracts. Okay, so depending upon the diffraction angle, you will be able to see a particular cone. So this is called Debye cone. You will be able to get a Debye cone. So since the sample is here, the X-ray is going, so thousands of randomly oriented crystal that falls on this light, this X-ray will fall on the thousands of the crystal of this sample, and since a polycrystalline, you will be able to see many cones you will be able to see. Depending upon the 2 theta value, you will see different angles. Okay, different cones you will be able to see. Only small fraction of crystallite actually, if you see here that all the diffraction plane will go out. Only this is the first hole, the end hole. This is the ring that formed on the film. So from this ring, so that what you used to do. So if you see these two rings are here, then that if you know that arc length S1 and W is the length, this level you know, then what will happen by using this theta, you can able to kind of find out by pi S1 by 2W, the front reflection and back reflection will be this. But this part was nowadays in more, this is based on earlier powder X-ray diffraction, where you have a projector that on the bottom you take a big this graph paper and then you draw those type of thing that it takes more than 1 hour, 2 hours to just get a spectra, which nowadays you are getting in 2 minutes, a very good spectra. So then by using this equation, that Bragg's law L lambda 2d sine theta, if you get the theta here, then you can able to find out all, for cubic system, d cubic will be a by h square plus k square plus l square. So s square plus k square plus l square equal to that you can find out 4a square lambda by sine square theta. So from this h square plus l square is proportional to sine square theta. So depending on theta, so h square plus l square is proportional to theta. So that equation you can find out, that we'll discuss how to identify. So this I have already discussed, that incoming X-ray is coming here. This is your sample surface, and diffraction ring is forming a UL sphere here. That beam. So whatever the beam is, you are getting P point. So you'll able to see that HKL in that plane, you'll able to see. So as I discussed this, so if you see, so if you identify a crystal structure, for example, you got a spectra, X-ray pattern you got, and from the X-ray pattern, now you identify whether it is a FCC structure or a BCC structure or a simple cubic structure. For that, you have to use that h square plus k square plus l square, that extinction rule, that you have to see how it's following. So if you see that I got a peak at 19, 22, 33, and so on, that we got a peak, and corresponding sine theta or sine square theta is 0.1, you can find out 0.15, 0.3 sine square theta, you can find out easily from sine theta. Then you see what is the minimum sine square theta. So minimum value is my 0.11. So sine square theta by sine square theta minimum, you get that 1.38 like this you get. So after getting this, so now you have to get his nearest whole number. You have to multiply it with a number, so that you will get a nearest whole number. Like here, if you see this 1.33, I multiply 3. Here you have to see randomly, you have to see 1, 2, 3. So if you multiply 3, then it's coming 3, 4.08, 8.1, 10.9, and so on. So you can, if you see the h square plus l square, k square plus l square, so you know that if it is 1, 1, 1, so it will be, you will get 3. So if you then this nearest number will be 1, 1, 1, 0, 0, 2. So you'll get a 4. So I have just after getting this, I have run this whole number, nearest whole number we got here 3, 4, 8, is 10.9 into 11, 12, and so on. So now, so you can see the 3, 4, 8, how you can express HKL value. 1, 1, 1 will be 3. So 2, 2, 0 will give you 4 s square plus k square plus l square, and 4, 0, 0 will give 16. So then after getting this HKL plane, you can see here, so once you get sine theta HKL plane, you can always, by putting this equation, you can get the D spacing, and then you can get the lattice parameter. So the lattice parameter, if you see, is coming 4.0, 3.9. So all are constant almost. So this is a constant. That means H equal to K equal to L here. So you will get FCC structures. So you can identify easily what is my crystal structure. Indexing is possible by using these simple techniques. Okay. Similarly, if you have a non-cubic system, that you have to take all these hexagonal system, you have a C axis will come. So S square plus HK plus K square by S square, and L square by C square will come. So you have the two terminology that this is 1 and this is L square by 1 here. So where you know hexagonal system A and Cy are constant, then if you see 4 by 3 S square to the H K 0 0 and L square by C by 0 0 L. So accordingly you can find out your what is the crystal structure. Similarly, tetragonal orthorhombic, you can able to identify their crystal structure by using this method. But if you see the powder diffraction method, that that this is a schematic of a X-ray diffractometer. You have a sample source here. This is the sample source where you're keeping your sample. Then you have the X-ray tube. From the X-ray tube, you are getting the X-ray. It's coming from the X-ray coming and falling on the sample surface. And then in between, then you have a slits, divergent slits and solar slits. And then with passing through different slits, it will fall into the secondary monochromator, from which it will go to the detector. Okay. So now the detector will identify those peaks and will give you the diffraction pattern. So you have a source requirement, you have a sample, you have a filter is there, then various slits, mirrors, and detector is there. So you will see individually each of these component, but mostly for the source we take copper source, that the tungsten filament, from where by thermonic emission we get electron which interact with the anode, that is copper anode, and remove that copper K alpha will come out and fall the sample surface. Then it will go to the passing through different stages, go to the detector, and your detector and the source are the important component of the X-ray diffraction pattern. So we will see that individually also. So if you see the powder diffraction instrumental setup, you can see here you have a sample tube here, X-ray tube, sorry, X-ray source, and you have a sample here and detector here. You can see they are in a in a particular circle. So that means this the sample is the center, and with the radius of this X-ray tubes and detector are the perimeter, the surface of this circle. So this powder diffraction, that circle is called Bragg-Banton geometry. So that X-ray tube and this source and detector, they should be arranged in this way. So like your X-ray tube moves theta, then again this will move to detector will move. So there is a theta to theta instrument. So where source is fixed, this source will be fixed. Only theta sample rotates theta degree, and that is a possible that one source can be fixed, sample can rotate, and detector can rotate. This will rotate theta, this will rotate theta. So both will rotate to theta then. So this is theta to theta instruments. But in this case, if sample is rotating, the problem is a powder sample, it may fall down. So their case, in the you can't use the theta to theta instrument. So you have to go for a theta instrument where sample is fixed. You can see sample is fixed and source will move you theta and detector will move you theta. So there will be theta instrument. Here, the diffraction is always normal. If you see the diffraction being this is this focusing circle, that the diffraction vector, this is always normal to the sample surface, and the bisect the angle. This bisect that angle, the sample to detector. So user can choose to move the sample and detector in field source, or detector and source in sample stage if sample stage is mixed at the same time. So what is the maximum theta is possible experimental? You can see here theta is moving, detector is moving theta, and source is also moving theta in case of theta. So maximum angle, so if you take it to here, it's 90 degree. So beyond that it's not possible. So maximum theta, that's why in case of 2 theta, mostly 140, 160, you can able to get the 2 theta value, where theta can be changed up to 70 to 80 degree. That is the maximum. Otherwise, both detector source, they will collide each other. You can't go. That is the maximum thing you can take. So we'll come to that different. There are different X-ray detectors. So I will discuss. We will take 2-3 minute break here. Then we will discuss that. What are the different detector source and then what are the information we'll get from the X-ray diffraction studies. If there is any question, you can raise, you can directly ask, or you can raise on the chat box.
So can we ask directly? Do we need to have it in chat box?
Yeah, you can directly ask.
So why is like when we see the Bragg equation and all, we see sine theta, like everything is in terms of is a function of theta. So why
Yeah.
is the value 2 theta so important that in so many papers when it comes to diffraction, we see 2 theta value more often than theta value?
See, generally does not express in theta value, it's always in 2 theta. Okay, so that is because that see, if you take that is in some with respect to your if I come to that, okay, with respect to that source, if source and the sample and this detector, they are in a fixed circle. If this sample moves theta, detectors move again theta. So in all total, there is a 2 theta movement from the incident ray. That the X from the if you see that generally we don't take from the sample, from sample to detector, that angle will be theta. But with respect to incident beam, if that is completely transmitted through the sample, so then that will again make theta angle. So this theta and this theta, so that we take 2 theta value. Okay. So that gives more accuracy, because if you take theta, that sometimes what happens that measurement when we here it is powder diffraction in theta to theta is possible, but if you take a small angle X-ray or something, so there is angle is very low, so it's not possible. So generally it's better to take a 2 theta is the better expression.
So the 2 theta is the angle between the
Incident.
source, the crystal and the detector.
Yeah, from the source to the detector, but that source has to be that the incident line is from transmitted. Okay, so like if I draw it, I will go to PPT. Okay, so if you see here, if you see, this is your sample, this is your source, and this is your sample, and this is detector. Okay, so if the incident line is completely transmitted, it will go like this, but it is diffracting from here. Okay, so angle the 2 theta is from this transmitted beam to the detector. This is 2 theta. So if you take in between here, from here it will be, this will be theta, this will be theta. So instead of taking this measurement, since both is rotating, sample is rotating, so we generally what we the software what you get, we get a 2 theta instead of theta. Okay.
Uh, but sir, in the X-ray diffraction experiment that I had witnessed, the sample was like in which axis is the sample rotating? Because it can't rotate horizontal vertically.
See,
It has
sample
to
is
rotate.
normally common XRD sample remains fixed. So in the powder sample, generally we take this theta instrument. So sample is fixed, that source is detector is moving. But if you go to single crystal XRD, there sample will move, source will move, detector will move. Again the stage will move. There will be a 4 angle or 5 angle rotation is there in case of single crystal XRD. But in powder XRD, there is only that this source and detector are moving.
So there can be a 3D mapping in the case of single crystal, but not for powder diffraction.
Yeah, the powder diffraction you won't get, you can't get a 3D mapping.
Okay.
3D mapping is only possible in case of single crystal excited.
Okay.
Okay, we start. So if you see like source X-ray detector is another important things. So in X-ray the instrumentation part, so there is a different types of detector, like point detectors are there, line detectors are there, and area detector. So point detector means it will take the data from each and individual point. In line, it scan along a line. That is the position sensitive detector. And in 2D array or in CCD plate, nowadays the charge coupled plates are there, even old age photographic film, those are area detectors. So if you see that this area detector, they will take the image, the 2D area detector mainly observe photons scattered along conic sections. Mostly this, most of this X-ray, either they are in point detector, observe one point of a space at a time. It's slow process, but in line detector, observe all point in a scattered along the line from 2 to 10 degree long. So like that, accordingly you have to select depending upon the ability of the X-ray to ionize mature, you can use the different detectors like GM counter detector earlier they used, then professional counter detector, and scintillator detector you can use some thallium iodide, sodium thallium iodide, and then silicon lithium, that silly, that semiconductor detector. So there are different types of detector you can use. And if you see the commonly used GM counter in the professional detector, there. So here it counts all photons within the energy. Like if you can see your X-ray is coming here, and this falls on this window. So in this here, krypton, argon, xenon with quenching gas, like some of these gas molecules are inside there. So they, the X-ray, after, coming from this, it will ionize their position, and depending upon that ionization, the amplification factor, you can get ionizing chamber, professional counter, GM counter. So mostly we use in X-ray diffraction either, professional or GM counter position. If you see the scintillator detector, you have a X-ray light coming and falling on a, you have a sodium iodide thallium layer is here. So the sodium iodide thallium, once that X-ray fall on this, what will happen from here, that electrons will emit. So from this light X-ray will produce some electron, and then this electron will go to the photocathode. Inside the photocathode, there are multiple anodes are there. They're called dinodes. Like one anode is here, another is here, then this and this, like multiple anodes are there. If one electron is coming here, here is divided into 2, then into 4, 8, 16, and so on. So at the end, you will get an avalanche of, this electrons you will get. So that using this type of sodium iodide thallium detector, what will happen, that X-ray, that even the low intensity, you can amplify it and you can able to get, finally that by photomultiplier tube will give you, final, energy resolution more than professional counter, but you'll get all those diffraction patterns. And if you see the diffraction pattern in commonly used material, like there is a liquid, there is a gas, and there is a crystal. So if you take a liquid monoatomic gas, in gas there is, the atoms are far away from each other in a gas molecule. So here that intensity will monotonically it will decrease. You will not get any periodic array is not there. You will not able to get diffraction pattern. But in case of liquid, you will get a liquid amorphous crystal. If there is a short range ordering, because of short range ordering, you will get a humps at around 2 theta at around this 27, 28 degree. You will get 25 to 27 here. You will get a broad peak. So that means that in case of crystal, here you will get sharp peak, because here the atoms are arranged periodically. They are very closely spacing to each other. Here there is a long range ordering, but in case of the amorphous material, there is no, there is a random orientation of, there is random arrangement of atoms. There is no, but for a short range they may be ordered. So because of the short range ordering, you are getting a broad peak. There is no long range ordering, so you will not get it's like the sharp peak in crystalline material. You will not get in amorphous. But in X-ray can be possible in two ways. So commonly in solid sample used in reflection method, like X-ray is coming here and going back, scattering back. Okay, but in case of the liquid sample, it's possible to do X-ray in a transmission mode. Like you can keep a liquid here, from the liquid that X-ray can transmit it through this liquid and then go to the detector. So that is only mostly used in liquid sample, but in solid sample we go for a this reflection mode. It's amorphous metal, a glass don't have periodic array with a long range periodicity, so you will not get a diffraction pattern. If you see a single crystal and a polycrystal material, in single crystal you can see here is the reentness. In single crystal, so all atoms are oriented in one direction. Like there will be only one plane or only 100 plane in that particular crystal. For a single crystal, there is one orientation in real place. All are oriented in one direction, you can see. So because of this, the reciprocal points are resolved, which we will get a similar, the reciprocal pattern will get all are arranged in a periodic array. That is the case of single crystal. Like if you see here, this is a single crystal, all planes are oriented in one direction. So incident beam is common diffracted in one direction. What you will get? You will get spot pattern instead of multiple beam. You will get spot pattern in case of in particular plane in case of single crystal. But if you take you can see here that this is a single crystal specimen I have taken here, and this is the oriented plane. If you see here, that is 100 plane, and incident beam is coming here in diffracted. 2 theta is satisfied. You are able to see that 100 plane. Okay, a single crystal specimen in black band diffraction would produce only family of peaks. Like if you see the peaks here, this one you are getting the peak here. This peak is here 100. Then you are getting a peak at 200. You are not getting 110, 111, 210. So they are empty. There is no peak here. There is no peak. Okay, so because this plane is oriented to the only one plane is there, the X-ray beam is oriented to that plane, and you are getting 100 plane. Similarly, you will also get its higher order plane. You will be able to get in case of a single crystal. But if you will take a polycrystal material, you can see here in a chunk of sample, you can see there are many planes. Like these are some black planes are there, some blue planes are there. If the incident beam falling on the blue plane, they will oriented in one direction. So like plane falling on the black plane, they will oriented to other direction. So because of that, so you will get corresponding to blue plane, you will get one dot for one plane. But there are multiple same plane will multiple will be there, so you will get many dots, and finally you will get a ring. But so for a black plane, you will get black plane, you will get another dots, and finally the multiple black planes are there. So depending upon the orientation, you will able to see here. You can see here that this blue plane here we have marked, and this 100 plane is diffracting here. 2 theta equation satisfying, we are getting a peak. Again in kept 110 is side rotated, another crystal is here, that is matching with 110, you are getting that peak. So similarly in this case 200, you are getting a peak. So multiple peaks you are able to see. So in case of a polycrystalline material, for every set of plane, there will be a small percentage of crystallite that properly oriented to diffract. Like there are many planes are there. So you have thousands of crystals in a polycrystalline material. So they all will orientate, and you will give you but all different peak is possible here. So if you see the common diffraction pattern, you can see here, this is I have shown here the excited pattern of zinc oxide that exists in zinc Ujjayi structure, the hexagonal, or zinc plane structure, or a nano tetrapod structure. You can see here in zinc plane, you are getting 111 and 002 plane. But in the Ujjayi, you have a 3 set of planes, 010, 002, and 011 plane. But in case of a nano tetrapod, what you are getting a peak with broad peak, you are getting this nano. So if you see that you can identify easily whether crystal structure is Ujjayi or it's a zinc blend from the crystal plane. So this kind of identification of hedges can be possible with the help of X-ray diffraction patterns. So if you see, how do you analyze? Once you get a diffraction pattern from XRD, the next step is to see how to identify that. So I have given a spectra here. You can see that it's intensity versus 2 theta, and this is my that peak position I have given at 27 on peak and 31, 45 and around 56. So all peaks have identified. Okay, in these peaks, what I identified, there is a different despacing and intensity I have shown. So my maximum intensity peak is at 31.7 and the other peaks are there. Okay, so after getting this, so first I have to see there is a database available, either it's called JCPDS, Joint Committee for Powder Diffraction Society, or ICDD, International Committee for Diffraction, ICDD. So either any of the two you can take, and then you can see how to analyze. So first, what I will do, I will see all these, whatever in the JCPDS file, I will see these despacing, existing despacing, what are the elements are there. So I found these are the element like ERCQ with despacing this, NaCl with despacing this, ammonium tungsten oxychloride despacing this, and another one is this. So now after getting this database from the JCPDS, I will see how my data point are matching. If I see here, your 2.8 to 1.96, 2.26. So there is third is again different. So I have to see minimum. The second one you see 2.82, 2.82 is my most intense, then 1.99, then 1.63. So these three is coming here, and in all these cases is not coming. So this is the one that first that set of plane that is coming close to each other. Identify the first three strongest plane, D1 this, D2 and D3. Search JCPDS manually. So there is a 2.84 and 2.80 plus or minus 0.02, plus or minus 0.02 we have to see that the variation, and I have got this plane, and from that since we have the up to third element, third despacing is matching with this NaCl, so my crystal structure is NaCl. Just this XRD pattern which corresponds to NH, this is nothing but this is NaCl. So you can identify any XRD pattern by using diffraction, X-ray diffraction, and you do the help of your JCPDS. So first you can identify the phase. Once you identify that you want to prepare a zinc oxide and you got it by analyzing with either with earlier available literature or with JCPDS database or ICC database, then now my sample has been successfully prepared. So I want to get more information. What are the other information I will get? So generally, if you see in diffraction pattern, your intensity is here and 2 theta. So you get this type of peak. Okay, this type of peak. So in this peak, there is a width is there involved. This width is there. This width is there. So what information I can get from peak broadening? So how that peak is getting broadened? But if you see the perfect XRD pattern with a bulk material, instead of this, what you will get a delta function like delta, like this type of intensity versus 2 theta. You will get only sharp line. There will be no peak, only sharp line you will get. In case of perfectly bulk material. But if you go to smaller and smaller side, like nanomaterial, instead of bulk, you get a broad type of pattern. So what you get? You get this type of broad pattern you can see here. So this broad pattern is mixing up many things. That means you have a broadening is due to one is instrumental broadening. That is how your instrument is alpha 1, alpha 2 peaks are there, how monochromaticity of your light, of your X-ray source, whether it's properly focused or not, that will give you instrumentation broadening, BI, and then there is a crystallite size. When you go to smaller and smaller, your peak will get broadened, you will get BC, the crystallites, and then when you go to formation from nanocyte particle, you will build up many strain in the lattice, and this strain will come and that will give you strain factor. And then if there is defects are there, like stacking fault or those type of defect, they will also contribute another defect. So all total, your peak broadening will be summation of your instrumental broadening, strain, whether it's instrumental strain, crystallite, all those things we get. So from the line broadening, if you separate out the instrumental broadening, then you will able to get the strain and crystallite size. You can calculate from the displacing. So once you get a X-ray diffraction pattern, you fit it properly either with Gaussian or Lorentzian. You have to see which model is fitting best depending upon your instrument. If it's Gaussian, you have to take BR square, B square minus BI, this is instrumentation line broadening. That means you have to take a silicon wafer and you have to take XRD pattern of the silicon. The silicon generally at 28, you will get a sharp peak, 28 degree. But instead of this, if your instrument is giving like this peak, so that this may be the broadening due to instrumentation. Generally, you get about 0.07 to 0.08 is the instrumental broadening. So that broadening has to your bit that this width you have to take B, and from there, if it is corresponding to Gaussian fitting, so B sample minus B instrumentation you have to subtract. If it is Lorentz, if it geometric means it follows it's Lorentzian one, then you have to use this type of equation. So once you subtracted the instrumental line broadening, and then you will get you will get a sharp peak. So in addition to the proper sampling has to be done also, because otherwise the proper sampling is not done. So one plane is coming here, other is here. So that will also contribute to the error factor, instrumental error. So all those instrumental error misalignment has to be removed so that you get less error. And then once you fitted properly, this is the peak. You fitted, you get FWHM. This is nothing but FWHM, full width at a half maxima. So that means this is your peak, this is full width, this is the peak height, this is the maximum peak height, at a half width here. So full width at half maxima. So peak intensity at half and width you have to find out. And then by using this error formula, so you can calculate beta and this K lambda by L cos theta. So your particle size will be your D equal to 0.89 lambda by beta cos theta. So K is equal to taken as a 0.89 lambda, generally assuming it is spherical particles. So you can calculate the particle size using this equation. You can calculate strain using 4 epsilon tan theta. This is strain. So you can calculate easily your crystallite size and your particle and your strain from this peak broadening. So when you go for peak broadening, you can see here, this is your crystallite size varying like this, and this is your beta strain. So always you take a lower angle peak so that beta crystallite and beta strain they lie separately. So if you take higher angle peak, so they are closer to each other. So smaller angle peaks should be used to separate beta strain and beta crystallite stage. You can able to get, but whole the error formula you are assuming your particle is spherical. And this equation is only valid, Faraday equation is only valid when particle is considered as spherical, and it can't valid bigger particle. Particle has more than 100 nanometer, your Faraday equation is not valid. So, so you can't use Faraday equation for bulk crystallite size calculation. So another method of calculating strain and crystallite size is Wilson-Hall plot. So here you have to put beta cos theta versus sin theta, and then you feed a straight line to the data from the slope and intercept. If that is C epsilon tan theta and K lambda by L cos theta. So that will be rearranged. So beta cos theta equal to strain C into epsilon sin theta by K lambda by L. So from one you will get, from slope you will get a strain, and from that particle size you will get from intercept. Okay, so you can see here, this is a bulk area and a nanocrystalline area. So bulk area is how sharp big blue line is observed. In case of nano, how the line broadening is occur. So this type of information you can get from this XRD. In addition to other dislocation, stacking fault information, all those you can see here the lattice plane is going straight. But here you can see the lattice plane is bent here, and one lattice plane is going and come closed here. So this is nothing but dislocation. So those type of information you can also get from diffraction information, whether there is a grain surface reflection or solid solution inhomogeneity. Like if you see, I have given one example here. You can see that the solid solution, that if I cerium oxide I'll take zirconia oxide. My cerium will give this blue peak and zirconia will give my red peak. When you make a solution limit, like I prepared a cerium zirconia O2, cerium X zirconia 1 minus X O2. So then you will say you will get a peak like this, black one, like it go like here, then this noise, and you get this. So you have to identify that to the solid solution homogeneity or solution limit by using this X-ray diffraction method. If you have a strain, like you can calculate, you can see this is D0, no strain, this is D spacing, no strain, you are getting a highly symmetric peak. If the uniform strain in one direction, like longitudinal here is shifted, here D1 is greater than D0, this elongated in one direction, your peak is getting shifted. If it is both ways, both D1 and D2 are changing your top and down, you are getting a diffraction spectrum is getting coherent here. So those type of information you get. Microstrain, like in this strain, there are multiple things are there, multiple effects. So all those effects microstrain produce peak broadening, so that you can identify. So after getting the information about your phase is formed by using seeing your JCPDS data, then getting lattice strain and particle size, what the next information you will get. So you can get the information intensity. From the intensity of the peak, why 100 peak is more intense, why is 111 is less. By those intensity, you can also identify some other things like you can find out. So that we'll discuss now. So if you see a crystal composed of unit cell, and inside unit cell you have atoms, and then these atoms are surrounded with electrons. So there is a scattering. When you see the scattering from a unit cell or scattering from a crystal, that means your diaphragm X-ray beam is scattering from a particular unit cell, then scattering from atom, and then scattering from electrons. Then sum of electronic factor, if you mix, you will join together, you will get an atomic structure factor, that is from atoms, then from unit cell, that's called structure factor. So electrons, what are the scattering from electron, you will get due to that is called polarization factor, and then scattering from atoms, whatever the atoms is present there, like if you see here, yeah, you can see here is a BC cubic structure. These are the atoms. So when you say unit cell, the whole thing you have to see. When I'm saying atom, this particular atom position I'm taking here. So in that case, if you see that they have a scattering from electron, scattering from atom, then scattering from a unit cell. So many atoms compose the whole unit cell. So intensity of HKL plane, particular plane, is proportional to scattering factor of that HKL plane. So the intensity is proportional to HKL. That means how atoms are arranged in a particular crystal structure, whether atoms are HCC arranged, whether BCC, whether HCP. So depending upon the atomic arrangement, you can able to get the intensity. So if you see that these are the atoms here, you can see that F, that structure, this is that scattering factor from electron, I is mainly proportional to 1 plus this cos square 2 theta, that is polarization factor mainly. But if you see the atomic scattering factor, the F, atomic scattering factor equal to amplitude of wave scattered by an atom divided by amplitude of wave scattered by an electron. So you are dividing whole atom scattering factor with respect to an electron. So here, if you see the scattering factor of an atom, that depend on sine theta by lambda. This is the sine theta by lambda. If you see how the structure factor is scattering is changing, like bromine, iodine, iron, chlorine, carbon, if you take in all case, your scattering factor is decreasing. As I told in first class that in case of X-ray, that if you take a diffraction pattern, intensity and 2 theta, at low angle you get most intense peak, at higher angle your peak intensity gets reduced. That is mainly because of the scattering of the atomic scattering factor depend upon the sine theta by lambda. And that is decreasing with respect to sine theta by lambda, your scattering factor is reducing. Because of that, your peak intensity is decreasing. But in case of neutron diffraction, this is in XRD, but in neutron diffraction that we'll discuss later, they are random. There you can higher angle, you can also get most intense peak. That is mainly because here there is no dependency on sine theta by lambda. There is, instead of that, that is depends on scattering length, which randomly varies. Okay. So this is the scattering factor. So total scattering factor, if you see, the scattering of electron has to add it to give you scattering factor of atom. Then the atom, if you take whole atom, you will to the particular crystal structure, that FCC or BCC, so that the form factor that you take that this unit cell structure factor, if you see, so the structure factor will be f h scale, the summation of f into e to the power minus 2 pi I h x n k y n l l z n. This k h scale is the atom position, and this f is your electronic factor, that fn, then it's the structure factor is coming here. So total that amplitude of wave scattered by all atoms of the unit cell divided by amplitude of wave factor, wave scattered by a single electron. So then you will get the whole structure factor. You can find out the density by dividing total volume. You can able to find out the density, and then what you see, if you say the structure factor, you calculate for simple cubic. If you see here, these are some of the equations that taken into consideration. So structure factor F equal to depend upon the only electronic one in case of this. So F equal to F square independent of scattering from HKL plane. So atoms are here. So the atoms at 0, 0 position. So because of that, if you do 0, 0 position, you put, so F equal to F square, scattering plane main. But if you take FCC structure, this is most will be F square equal to 16 F square, means if you have a HKL unmixed or HKL mixed, that will give you 0, 1, 0, 0, 2, 1, 1 here. With the mixed, on the mixed one, your scattering factor is 0. But only this type of plane 1, 1, 1, 2, 0, 0, 1 HKL is unmixed. So then you will get a real scattering factor, that is in case of this FCC. So I am not discussing them in detail this way. So you can go through some books, I will suggest. So if you see the structure factor as I discussed, NaCl and KCl, why NaCl 1, 1 and peak, you can able to see here that KCl, I told it's missing here. So that in case of KCl, not this one. So this one is the 1, 1, 1 that is absent here. Here you are getting a peak pregnancy. Here it is absent. So that is mainly, as I told, that the isoelectronic, being that isoelectronic nature K and Cl, they're isoelectronic. So what are the scattering intensity, that scattering factor coming from this F, that 4K will come from K atom and 4Cl will come from this, they will all will equal and they will cancel out, you'll get to 0. Because isoelectronic, they will cancel. But in case of NaCl, if there is all even with 4Na plus 4KCl, but here it is minus. So here there is net is present, so you are getting a small peak, but here it is absent. So that's why you are not getting NaCl, KCl peak. So now from this you can, from the structure factor, you can now able to say whether that particular like isoelectronic effect is there or not. Those information you can get. So total intensity, if you see, but I discussed one structure factor only. The structure factor is there. In addition, there is multiplicity factor, means many family of like 1, 0, 0 planes. Similarly, 0, 0, 1, 0, 1, 0, minus 1, 0, 0, 0, minus 1, 0, or 0, 0, minus. So the 6th family of 1, 0, 0, 6. So that the multiplicity will come into picture. Then polarization, that wave polarization will come into picture. And then Lorentz, that is geometric factor, like when you are doing some this all this alignment, all those things, how this arrangement of this lens, this slits and all those things, that will give you Lorentz factor positioning. Then there is absorption factor, because sample may heated off. As I told, some IR radiation can emit, so that sample can be heated off. So that will 1 by 2 mu will take, then temperature effect, diffuse scattering, there device scattering will be there. So total intensity I equal to the summation of this intensity, this polarization factor, and this or structure factor, and all other factor together. This is your polarization factor, and this is your 1 by 2 is your absorption factor, and this is your diffuse scattering. So total intensity is this. Now, since you know the total intensity, you can identify, from the intensity by doing root field analysis, you can able to, find out the different space groups. Then you can find out their, that crystal parameter, all those things like A, B, C, or lattice parameter. Then this other information you can able to find out. For example, if you see that if a mixture of phases, like you can see, this is a quartz, this is a cristobalite, this is a glass. So glass exists in these three forms. The glass exists in amorphous, and a cristobalite and a fast phase. So this is individually they are phase like this. You will get a amorphous phase in case of glass, and that's crystalline phase in these two. But if you get a mixture of that, you can see is amorphous the glass is there, and then you have a sharp peak is there. So those type of identification can be done by using X-ray diffraction. You can analyze how much percentage of your amorphous, what is the percentage of crystallinity that you can find out. If you see the Al2O3 TiO2 is mixture phase, this is Al2O3 the TiO2, you can find out the composition. And if you do the XRD for accuracy, you can find out that also. So what crystalline phase is formed from XRD, so far you discussed, you can find out what is the crystalline phase formed, how much each crystalline phase is mixture, what are the component of Al2O3, what is the component of TiO2, that you can find out. If there is an amorphous like here, silica is there, so whether that is present or absent, that you can find out. So with proper calibration, you can find out each of the phase. And that calibration can be done by using that with known element like the high quality data. We can quantify each phase. It must identify the ratio of the peak intensity is very linearly as the weight fraction of two components. If I have intensity of alpha component and beta component there, so they will vary with this weight fraction of K alpha, X alpha and that beta. So it is proportional to the linearly proportional to the weight fraction of individual. And if you have a reference intensity ratio, that if you have a proper reference material you have, that from the reference material you can draw a linear curve, and then you can quantify each element by using this X-ray diffraction technique. Okay, so the whole pattern, the rotable refinement canal will do that is SA, that is the retrieval scale factor, that is the scattering from all the summation of all that polarization, temperature, this atom structure factor, everything divided by mass and volume of that element, you can find out this component. So I will not discuss in detail about root-will analysis because of time constraint. So by using a proper root-will method, that there is a fundamental calculation from crystal structure, you can produce model to produce a calculated diffraction. But like by using theoretical data, with a peak position and your whether it's FCC, BCC, based on your knowledge, by using root-will analysis, you can draw with calculation, with fundamental calculation from crystal structure model to produce a calculated diffraction pattern. Then your calculated diffraction pattern and your obtained diffraction you can compare. You can find out how much deviate from that. So it's based on the least square based minimization agglomerating method. So you need a starting model to actualize. So there are in the currently available software like you do foolproof or something, you can get a starting model. You choose your model, and by using that model, you can able to analyze all those parameters. You can get crystal structure, microstrain, preferred orientation, peak position, intensity, everything you can able to get from the root-will analysis. And that whether that your analysis is best or not, you can identify whether by a quality structure refinement factor, residual index or R factor, that F0 minus FC by F0, that this is your from calculated to the this original obtained parameter you can find out. And then if you see the whole root-will formula, you can see that is the structure factor here, this is the multiplicity factor, this is polarization factor is there. Then you have a other, this is the observed YB. So all these parameters, they are scaling, SF is scaling factor, then multiplicity, then value preferred orientation factor PK, and F square is your, this is your the structure factor, then your LP is origin factor, theta peak profile function, and phi, all those parameters taken. By using first you have to take a suitable crystal model from the software, then crystal system in units, a dimension what you obtain from your XRD that you provide, full database you insert, then Brevis lattice mention, space group, constant once you get, you finally refinement will able to get. And what you will get here, you can see an example here that this is the monoclinic crystal structure of lithium, magnesium, borate, something borate. You can see here the red one, that is why you observe, and y calculated is the line one here, and this is the y observed minus y calculated. You can get a differentiation. You can from this analysis you can able to get lattice parameter A, B, C, and then you have a kind of the volume, density, all those information, space group you can able to identify. If you see here, it gives you structure variables like you have to provide atom position, profile parameter, you are able to get then different correction things you have to give. So finally you'll able to get this. So it will help, determination of absolute crystal structure using a powder is quite difficult, mostly impossible, because you have a HKL and you have a minus HKL reflections. So for limited data with constraints can be necessary, like bond angle, bond length, and bond composition. If you get some information, so that will help you with starting model. You can able to identify proper crystal structures. Okay. So in today's class, what we mainly study. So the take home message is that we mainly cover that how X-ray diffraction instrumentation details and how it gives the X-ray pattern, and then what are the information you get. If you see from XRD, with the first thing you get phase determination that will give you a composition and your abundance. How much percentage is there, what is the composition, whether you prepare iron oxide, zinc oxide, or nickel or zinc nanoparticle, that can be identified by phase determination using XRD. So that is the phase determination is possible. Second, by using peak profiling here, by full width half maximum, you can able to get the crystal structure, and then lattice parameter by using that equation, whether simple cubic, FCC, SCP. So using that equations, you can able to using those equations, lattice parameter A, then you can calculate crystallite size, micro strain, what is the strain built up due to nanoparticle, for example, what is texture analysis, like whether it is a epitextural growth, like people will like why only 200, like if you take a thin film XRD, we will discuss next class. A thin film XRD, you will able to get mostly highly oriented in one direction, then you will get a particular that peak only. So its texture analysis can be possible. Then we'll discuss how this XRD will help. High temperature XRD is present there, high pressure XRD is there. So during heat treatment, when the phase changes from, like for example, monoclinic to orthorhombic or so on, so those type of phase change can be identified. Then you can apply the pressure with respect to pressure, how the phases or changes, those things you can identify. So the peak position will give you translational symmetry, namely what is the size, shape of the unit cell you will get from peak position, and from the peak intensity you will get about the electron density inside the unit cell, namely where the atom is located, whether FCC, BCC, the atom location you can easily find out by using peak intensity, and peak shape and width give you the information about perfect crystal. If it is perfect crystal, then you will get a sharp line peak. That is, this time instead of getting this, you will get only this peak in the XRD, but in case of nanophase, you will get a peak already. So these are the information mostly you will get from XRD instruments. So you can follow some of these books, like Solid State Chemistry and its Application by A.R. West. That is one of the good book for that cover most of the characterization techniques which I am going to cover in this module. And then you can also cover this, see this advanced technique for material characterization by K. Tyagi, M. Roy, and S. Kulushrestha, S. Banerjee. And so that book you can see that advanced technique, all characterization techniques other than what I will also cover that is there. Then even for XRD specifically, you can see this BD quality, the elements of X-ray diffraction, and also for there is another book, Material Characterization, Introduction to Microscopic and Spectroscopic Methods. So that is wire length. So this book also covers all techniques, some of these techniques required for characterization of your materials. Okay. So if there is any question, you can ask me, or you can otherwise you can also mail me. So, Okay, if there is no questions, we can end it here today. We will meet for next.
Hello.
Yes.
Sir, can redundant analysis can be performed on a XRD data of multiple pages? Is it possible?
Your voice is breaking. I'm not getting.
Can redundant analysis can be performed on the XRD data of multiple pages? Is it?
Your voice is not at all audible. So just put that question to me. My email ID is I'll answer to you because your voice is not at all audible. So what I'm getting that you want to know that the root wheel analysis can be done on some system or
For multiple pages.
yeah, for multiple plane, you can do root wheel analysis. That is possible, but it will take quite time, and you have to choose a suitable model. If you are able to choose a suitable starting model, like polycrystalline material, you can easily identify it. But if it's a mixture of phase, then it's not easy to do with this root wheel analysis. You will face a lot of difficulties in analyzing that.
So then what is the usual?
Excuse me, sir. May I ask one question?
Yes. Yes. Hello. Hello. Yeah. Hello. So, who was asking question? I think it was disconnected. So, next class we will discuss your question.
Yes, sir. Sorry, actually, due to network issues, I couldn't hear you properly. Sir, my
Okay.
question, today's explanation was great. I could learn many things about this XRD. It is totally clear. Thank you so much, sir, for this excellent teaching. Sir, one thing, will there be any, the slides will be provided to us?
Yeah. That I'll provide whatever the slides I am going through. All classes slide I will upload on Anuvidya site. Okay. So I'll request my colleague to upload all slides. So most probably by in next class you'll able to download all slides. Okay. And